Welcome back, lovely students. Let's get to it. We got another calculus problem coming your way. This one's extra fun, but we always have a little bit of implicit differentiation in here. If you have no idea what that means, keep watching, you'll learn. Let's get to it. So we've got the curve C defined by the equation y. There we go. Let's select the pen, otherwise this won't work. Y squared is equal to 2xy equals to 5 minus e to the x. There's our curve. Point A lies on C and it's evaluated at the point 0A. So first part, nice and simple, no calculus here. Can we figure out what A is? To do this, all we need to do is we need to plug in a 0 in for X and an A for Y, and we can solve for A in this particular case. So let's plug it in. A squared, well, 2 times 0 times whatever is always going to be a 0. So a squared is going to be equal to 5 minus e to the x. X is 0. So 5 minus e to the 0. E to the 0 cancels out to a 1. 5 minus 1 is 4. So a squared is equal to 4. If we take the square root of both of these sides, we can solve for a. A is equal to plus or minus 2. Notice, though, the question tells us that a can only take on positive values. So the negative value cannot stand. A is equal to only positive 2. There's a solution. First part, nice and easy, nothing crazy. Now part B, this is when it gets really fun. We have to show that the derivative of y is equal to that. The reason this is tricky is because we don't have an equation y equals something. We have an expression that has both x's and y's in them, so we have to differentiate this implicitly. To do this, we have to use kind of a chain rule embedded into our heads the whole time. We're going to take the derivative of each individual one of these components with respect to x. Okay, so let's start. I'm going to rewrite the equation here so we have it. Y squared minus 2xy is equal to 5 minus e to the x. Okay, so let's differentiate each one of these terms. The derivative of y squared we are going to write as 2y, because of the power rule, times dy dx, because we don't know what the derivative of y is, because we don't know what y is at all. So we can't differentiate with respect to x, therefore we leave it as dy dx. This is how implicit differentiation works. Minus the second component, we're going to take the 2 out and then take the derivative of x times y using the power rule. So the derivative of x times y is going to be equal to, derivative of x is 1, so 1 times y is just y, plus x times the derivative of y, which is dy dx. We differentiate that implicitly because we're differentiating with respect to x. So that's the derivative of that term there. On the other side of the equal sign, we've got our lives are a lot easier because we've got the derivative of 5, which is 0. So I'll even write it into 0 so we know it's there. Minus derivative of e to the x is just e to the x. Okay, let's simplify some stuff over on this left-hand side. So I've got 2y dy dx minus, I'm going to distribute this 2 now across all these terms. 2y minus 2x dy dx is equal to the negative e to the x. Now from here, I can move this 2y over to this side, and I can also factor out a dy dx term. This is when the implicit differentiation becomes very powerful. So if I factor out a dy dx term from this term and this term, what am I left with? I'm left with a 2y minus 2x. And on the other side of the equation, I moved that 2y over, so I added 2y to both sides. So we get 2y minus e to the x. And now, nice and simple, if I want to leave this dy dx term alone, I can just divide both sides of the equation by 2y minus 2x. That leaves dy dx all by itself. 2y minus e to the x, all divided by 2y minus x if I factor out the 2 term. And there you go. There's your derivative, 4 points in the back. Check. All right, let's do part C of this question together. Part C is asking us to find the equation of the normal to C at point A. To do that, we're going to use this expression for the derivative we came up with. First thing we need to do is we need to figure out what is the slope of the tangent at point A, which point A we were told at the very beginning is 0, 2, 2. I'm going to write it down here. 0, 2 is the point. So first thing I'm going to do in my new expression for the derivative, I'm going to plug in these 2 points for x and y. So let's just rewrite it here. 2y minus e to the x over 2 times y minus x. If I plug in 0 and 2 into this expression, I get 2 times 2 minus e to the 0 over 2 times 2 minus 0. Now we can simplify. 2 times 2 is 4. E to the 0 is 1. So 4 minus 1 over 4 gives me 3/4. That's going to be therefore the slope. If I were to draw a tangent to that curve at this point, that would be the slope of that line. So I would even write this as the m of the tangent. But we're not after that. We're after the slope of the normal. To get the normal, the slope of the normal is therefore just going to be the negative reciprocal of that, negative 4/3. Okay, that's the slope of that line. So now we're going to create an equation in the form y equals mx plus b, where m is equal to negative, let's do this, y is equal to negative 4/3 x plus b. To figure out b, in this case the constant, all we're going to do is we're going to plug in this point again, 0, 2. We're using that point quite a lot. If we plug in 0 and 2, we can figure out what b is, because anytime we need to figure out one component from an equation in a line, as long as we know one of the points, plug it in, see what b spits out. So if I plug in 2 and 0, I get negative 4/3 times 0 plus b. That term goes away. So we see that b is equal to 2. So the equation of the normal line for this expression is just negative 4/3 x plus 2. That is going to give me the equation to the normal at point A of the curve C. We're on part D. Part D is asking us to find the coordinates of the second point at which the normal that we just found, the expression to this guy, y equals negative 4/3 x plus 2, where does that intersect the curve C, the second point? So it's tangent to C, but it's basically telling us this curve has a bit of a weird shape and it touches the curve another point. Whenever we see the word intersect, we usually think, oh, we're going to set the equations equal to each other. In this case, we can't necessarily do that because the original equation we're given, if we highlight it here, it's not written in terms of y equals something. But what we can do is we can, since we have an expression for y, to set it equal or to find the intersect, what we can do is we can literally plug in, every time we see a y in the original equation, we can plug in negative 4/3 x plus 2. So let me rewrite the original equation here, part D. The original equation is y squared minus 2xy is equal to 5 minus e to the x. I believe that's correct, yes. So let's just go ahead and plug into this value. Every time we see a y, we're going to plug in this value. Okay, so I get negative 4/3 x plus 2 squared minus 2x, negative 4/3 x plus 2, there we go, is equal to 5 minus e to the x. Now, all we need to do is solve this. And to solve this, the easiest thing to do would be to plug this into a calculator, graph it, lots of different strategies since it's paper 2. So let's go ahead and do that. When I plug this into my calculator, I get that x is equal to 1.56. That's what makes this expression true. Then when I plug in x back into my original equation and figure out what y value it gives out, I get a y value of negative 0.078. So the second point at which this intersects the same curve is going to be at the coordinates 1.56 and negative 0.078. Last little bit, few last points to get, part E. Given that v is equal to y cubed, find dv dx at x equals 0. So given that v is equal to y cubed, we're looking for dv dx evaluated at x equals 0. Okay, to get this, we're going to use implicit differentiation again. The expression for dv dx is the same thing as we said. It would be the same as taking the derivative with respect to x of y cubed. Okay, let's use our implicit differentiation and chain rules. The derivative of y cubed with respect to x would be 3y squared times dy dx. We know what dy dx is though, because we got the expression for dy dx all the way up here. So let's zoom out a little bit and we can write it back down. So dy dx, this would be equal to 3y squared times dy dx is 2y minus e to the x over 2 times y minus x. That's my expression for dv dx. That's it. And now here we got to plug in x equals 0. And we know that x equals 0, that point occurs when y is equal to 2. So we got to plug in the coordinates 0 to 2 into this guy. Nothing crazy. So every time we see a y, we're going to plug in a 2, 3 times 2 squared. And every time we see an x, we're going to plug in a 0. 2 times 2 minus e to the 0 over 2 times 2 minus 0. This is going to be 4 minus 1. 4 minus 1 over 4, which is 3/4. So we can rewrite this as 3 over 4. And this first term, 3 times 2 squared. 2 squared is 4. 3 times 4 is 12. So we are left with 12 times 3/4. These guys are going to cancel out, leaving us with a 3 times 3, which is equal to 9. So we evaluated dv dx at x equals 0, and we get 9. That's it. Done and dusted. A bunch of points. How many points was that? That was a total of 16 marks on a question number 12 in an old IB HL paper 2. Tough question. You rocked it. If you like this video and you like more or you want more, like, comment, subscribe, do all that jazz. Would really appreciate the help. More content coming your way soon. See ya.